Here we're going to introduce conic sections and with a focus on parabolas for now. And it's important to remember that a conic section has a geometric definition and an algebraic definition. And why these definitions actually both produce the same sort of pictures is beyond the scope of this course, but or this video at least. But it's important to know that they do have, they essentially started in geometry, but can be moved to the XY plane where they can be described algebraically. So it's geometrically, a conic section is just a cross section of a cone, where we define a cone to be, two cones whose vertices are touching each other. And depending on how you take that cross section, you get different pictures. So you can get an ellipse, a parabola, hyperbola. You can even get a point, a line, or two intersecting lines, which those are degenerate cases that we're not going to focus on, mainly the top three. Algebraically, conic sections are the graphs of second-degree equations in two variables. And these are equations of the form below. And depending on which of these coefficients are zero, your picture will change, and the type of conic you produce in the XY plane will change. So let's start with parabolas. So we're going to begin with a parabola. Now each conic has its own unique definition within the XY plane, and from this definition, or this description, we're going to derive its unique algebraic equation. A parabola is a set of points in the plane equidistant from a particular line, called the directrix, and a particular point, called the focus. Above here you can see a horizontal line, that's the directrix, and then the black point is the focus. And all the points that are equidistant from the directrix and that focus traces out the parabola. And when I say the distance from the point on the parabola to the directrix, we're going to use the geometric definition, which is that perpendicular distance there. So a couple of terms. The distance from the directrix to the vertex of this parabola, that length p, is called the focal length. And the chord that runs through the focus and is parallel to the directrix here is called the focal width. So now that the focal width is has a length of 4p, is something that can be shown. It's kind of given away in this diagram here. But in any case, the one thing to notice is that the vertex is midway between the directrix and the focus, and it happens to be the closest point on the parabola to both the focus and the directrix. And we're going to see that value p ends up helping us find equations of parabolas. For now, let's go and derive the equation of a parabola from this description. So we know that the definition of a parabola is that it's the locus of points equidistant from a line called the directrix and a point called the focus. So we're going to use this definition to come up with an equation of a parabola whose vertex is at the origin. Now the way to do that is to pick an arbitrary point on the parabola, which we've done here. We called it xy. The distance between that point and the focus is d. Now we can come up with an expression for d. You can use the distance formula, and what I think I'll do, just to kind of revive a little bit of the essence of the distance formula, is I'm just going to make a right triangle there. So we can use the Pythagorean theorem if we can find the sides, or expression for the sides. So this horizontal distance here would just be, that's just the x-coordinate of the parabola, or of the point on the parabola, rather. Now if I want to express that as a positive distance, I'd have to say it's negative x, because x is a negative value. So that has length negative x, and this leg of the triangle is it's the distance between the right angle and the y-coordinate of the parabola. Well, this whole distance here is y, which means that we can get that distance by taking y and subtracting this distance, which I'll put in blue, which is p. So if that leg is y minus p. I'm just going to draw it a little better over here. So I've got, this is a length of negative x, this is a length of y minus p. And now the Pythagorean theorem can tell us that this length would be the square root of negative x squared, which I'll just call x squared, plus y minus p squared. So that's that distance. And we want that to be equal to the distance from the point on the parabola and the directrix. But that's easy because it's just the y coordinate. That's the distance from that point to the x-axis, plus the distance to the directrix, which is a distance of p. Or you could just subtract the coordinates, the y coordinates, y minus negative p. So if you put that together, you get this equation here. Y minus negative p, which is y plus p, the distance from the parabola to the directrix, is equal to the distance from the focus to the point on the parabola. Now you can imagine the first thing we're going to do here, because we're going to want to solve for y, is we're going to square both sides. So now I've got y plus p squared is equal to x squared plus y minus p all squared. Expanding, we'll get some things to cancel. So a couple nice things happen right away. We see that from both sides a y squared will cancel. We see that the p squareds will cancel. And you'll be left with an x squared. So I'm going to add 2yp to both sides. So now I've got 4yp is equal to x squared. And that just means if I solve for y, that y is equal to 1 over 4p times x squared. So what we found is an equation for a parabola whose vertex is at the origin, and you can see that this parabola's its focal width, I guess, is what we can call it. Again, that's the line segment through the focus parallel to the directrix. And in any case, how wide the parabola opens is going to be dependent on p, right? So it's an equation that depends on p, which is, again, that focal length. And so that's going to be, we're going to need that when we try to come up with equations based on descriptions. So I'm going to write that below these two pictures here, because that's our standard equation for parabolas that open up or down. And as many of you, I think, have had some experience with parabolas, if 1 over 4p happens to be negative, then you would be dealing with a parabola that opens down. So the focus here would have a coordinate 0p, and the directrix there we go, would have equation y equals negative p. All right. Now I'm not dealing with shifts here because we'll just use prior knowledge and we'll cross those bridges when they come in terms of shifts and things like that. But there's our standard equation of a parabola that opens up or down whose vertex is at the origin. If a parabola opens left or right, that's called the inverse relation. And that's because it results from just switching the x and y coordinates. So those equations would look like that. The focus, and actually, to be thorough, I really should have said the focus would be at 0 plus or minus p, and the directrix should have equation y plus or minus p. I didn't account for the negative for the direction that the parabola opens in that case. The focus, in this case though, would have coordinates plus or minus p 0, and the directrix would have equation x equal to plus or minus p. All right, and again, it's important to remember that the vertex of the parabola is always right directly in between the focus and the directrix. So keep that in mind as we try to solve or find equations based on descriptions.